by Taylor, and you see the title of the talk there.
Thank you. Well, let me first thank the organizers for putting on such a nice event. It's been very nice for me. You don't believe so? Maybe I just need to speak a bit louder. Is that helpful? Okay. Louder. Well, I was saying I wanted to thank the organizers because for me it's been very nice to come here. I'm really trained as a numerical analyst rather than as a statistician, so many of the takes on the material that I've been hearing are quite different than the way I've thought about things in the past, so it's been very, very useful. I'd like to begin by saying that a number of the results that I'll be presenting you have seen before. David Donahoe, this work is all in collaboration with David Donahoe. He spoke earlier on Monday, gave a beautiful presentation of the notion of breakdown points and phase diagrams. I'll be looking at the exact same thing, but I'll give you a bit more detail on a specific example. So hopefully the repetition won't be too much, and the extra detail will make clear what kind of advances we have. Also, as I was saying, I'm really more of a numerical analyst. So in my talk, capital N is the new P. There will be no notion of noise. I'll be looking at a very simple problem. So I'm going to be looking at, in some sense, what is lasso without noise. So we have an underdetermined system of equations, and we're going to be looking for the sparsest solution. Okay, very similar to what lasso is trying to do. We're going to solve it using the min L1. But again, because we're not going to have any noise, we're going to have exact equality for the constraints. And we're going to ask and try to come up with the answers as precisely as possible. The very simple question, how sparse does a signal need to be so that when we solve the L1 problem, we recover exactly the sparsest solution? This is very similar to the kind of results that not only Dave presented, but also Emmanuel presented and Martin Wainwright. So what we're going to be looking for is phase transitions in a domain. It's going to be a unit rectangle where we're looking at sparsity. K is going to be sparsity throughout my talk. Little n is going to be the number of measurements, and capital N is going to be the signal length. Maybe it's useful to write that up. So we have K for the sparsity, little n for the measurements, and capital N for the signal length. And we're going to consider the rectangle throughout this talk, where we're looking at two ratios, little n over big N and k over little n. This is going to be the unit square, 0 to 1. And we, of course, have the nesting for these variables that k, the information content, is going to be less than little n, less than or equal, and little n is going to be less than or equal to capital N. So one way of looking at the results we're going to be presenting is to develop a precise behavior for lasso in the case where we have no noise. Okay? So we've seen similar results already from Martin, but in the case of noise, where the coefficients are bounded away from 0. The way that Dave and I have been looking at these problems is through the theory of polytopes. This shouldn't be such a surprise, because since we're looking at the L1 norm, this is really the natural mathematical tool to be looking at the behavior of the L1 minimization. So the talk is going to go as follows. We're going to start by looking at some classical questions in geometry, and then we'll show what our results are essentially in that context. So statements about geometric properties, hence the title of the talk. And then we're going to move on, and we're going to come back to this question of lasso without noise, and we're going to show how these phase transitions behave. And then at the end, we'll wrap up with a few sort of cute takeaway applications. Okay, so what is the first notion that we want to talk about for convex polytopes? Well, this is what's called neighborliness. So what we're going to do is we're going to have points in R little n. This is the dimension of the space we're going to be looking at. We're going to have capital N points. We have more points than we have the dimension, and we're going to form the convex hull of this polytope. And then we're going to ask various questions. Well, for neighborliness, this is a property which is going to be somewhat similar to the kind of statements that you would have seen in Emmanuel's talk. we're going to talk about neighborliness where, first of all, zero neighborliness would be the case where we have all points from our convex hull, all the points that we drew, A, as vertices of the convex hull. So none of them fall interior. This, one can imagine, is certainly possible to be happening. Even in low dimension, we could imagine grabbing points on the sphere, and then it would, of course, be one neighborly. We could then move up to two neighborly. We could ask, well, we want to have all points. When we connect the line between those 2 points, we want this to also be exterior to the polytope. In low dimensions, this begins to seem implausible. So if we were to grab a point here and another point on the other side of the polytope, clearly this is going to go through the interior, and it's not going to be one neighborly, but there would be a few points such as this vertex and a nearby vertex, which would be on the exterior on the edge. But we all know from high dimensional geometry that our intuition in low dimensions is probably going to lead us astray, and that the behavior in high dimensions may be substantially different. Okay? The k neighborly would be just the generalization where we grab k minus one, where we grab k columns of A, we look at the k minus 1 face of the convex hull, and we ask that all k minus 1 faces of the convex, all k, when you grab any k columns and you construct the k minus 1 face, that is a face of the convex hull of A. Okay. Now, cyclic polytopes are known to be maximally neighborly. So these polytopes are neighborly with dimension little n divided by 2. So, of course, the most that we can hope would be a constant times little n, and the constant, it turns out, is 2. And these happen in the case of having von der Monde matrices. So there are matrices in high dimension which are extremely neighborly. Now, it was conjectured when researchers were first looking at these kinds of topics that, in some sense, if you were to randomly grab a polytope, we'll define what we mean by that a little later on, that it would in fact be neighborly. This was the belief. Now, there are a number of results which would suggest that that may not be the case. So let's first of all look at sort of the classical setting. So we're going to be grabbing our points in our points A, I, our capital N points. We're going to fix little n. And then we're going to keep adding points. Well, what happens as we keep adding points, Gaussian? Well, the number of vertices scales like log of capital N. So it's pretty clear. As you keep adding points, you're not going to be even zero neighborly. You're going to have very few, proportionally, of the points actually falling on the exterior. So we're not even achieving zero neighborly. So this might seem discouraging, but it turns out that when we look at a scaling which is proportional, so we're going to not fix little n, but we're going to let both grow, which is sort of the modern setting that we've heard about in many of the talks. So this is some ratio in 0 to 1. We'll look at what happens as this ratio goes to 0, but for now, let's just let it be fixed. So we have a fixed ratio. We're going to drive both variables off to infinity. And surprise, it turns out that Gale was correct. If we grab the points as, if we have the points in A coming from, say, a random ortho projector, or in this setting, we could have them be drawn Gaussian IID, then, in fact, it is going to be neighborly. And the neighborliness is going to be with a constant of proportionality to little n, which is, again, as good as we can really hope for. And that constant is what we were able to work out. So here's the constant, rho sub s. This plus, I'll come to what that means in a few moments. So there's a constant here dictated by that ratio of little n over big N. So if you were to pick the ratio of, say, a half, you could go up here and you could read off what this value is. It would give you a value of something like, say, 0.2, and you would say it's neighborly with proportionality constant 0.2. Okay. So this is the way of viewing the kind of results that we developed in the case of high-dimensional geometry. So how does this connect back with sparse approximation? Well, we're talking about vectors x in R capital N. So our vector that we're looking at for ax equals b, x is the vector of interest, so this would be normally the beta. And we're assuming that this is k sparse with k less than n. So that means that the x lives on a k minus 1 face of the L1 ball. Okay? So here's our L1 ball in R capital N. And let's say, for instance, it was composed of two non-zeros, this non-zero and that non-zero. Then where you were, which depending upon the weight of the non-zero entries, would tell you where you were on this edge. But you would be somewhere on this edge. So really, we're assuming Based upon our model, the signal lives on one of these low-dimensional edges. And then we're applying our random projector, A, to the L1 ball. And one of two things is going to happen to these edges. We're interested in these edges. Those are our sparse vectors. Either they're going to fall on the exterior of the convex hull of A here, or they could fall interior. So for instance, it could be this dotted line, which falls interior to the convex hull of A. Well, what does that mean for the sparse recovery problem? Well, any sparsity patterns, so notice we don't care about the particular entries in X, but any sparsity pattern in X so that it falls onto the exterior, so it remains an edge, it survives projection from R capital N down to R little n. That is a sparsity pattern for which, if we solve the L1 problem, we will recover exactly the sparsest solution. We'll recover the L0 problem. However, faces which fall interior are support sets which we simply cannot recover by solving the L1 problem. Whether that was our answer or not, it is a face, a support set, which will never be a solution. So one could view this, if you would like, as saying, okay, well, we have a point looking in the dual space. This would be B. This is the point that we're interested in recovering. And we have our convex hull. And now we grow it out. We could grow it instead of minimizing it. It makes the pictures a little bit easier. If it falls on the exterior edge, then we will recover the sparsity. So here, I think it's a bit difficult to see. Sorry about that. Maybe we should turn the lights off so these can be seen a little bit easier. Someone doesn't mind? Okay, that's a bit better. So if it did fall on the exterior, if that edge were preserved, did survive projection, then it would fall on the exterior, and that point B would be recovered. As you grew the polytope, it would intersect the edge of interest. However, if, for instance, on the prior drawing, here you had the edge which fell interior to the polytope, then what you would see is that rather than connecting with the edge that you were looking for, which was interior, it would end up giving you a solution which was on the highest dimensional face. So you would get a solution which had little n number of non-zeros. And that was what would happen with probability 1 if you were also were to perturb your solution B away from a sparse vector. Okay, so hopefully that convinces you that really what we do care about to understand this phenomena is the facial structure of the polytope A. So we want to understand how that behaves for random matrices. We're going to be looking at random orthoprojectors. So our work has a big debt to be paid to prior work by Affentranger and Schneider and Vershik and Sporyashev, who looked at these kinds of questions without really the motivation that we're looking at here for, say, lasso, but just in terms of understanding the underlying geometry. They worked out formulas for what is the discrepancy between the number of faces you start with for a polytope Q and the expected number of faces that you have for a random orthoprojector being applied to Q. Okay, so we have an explicit formula here, and Dave put this up the other day, showed you how that behaves. To give you an idea, again, you can see that it's composed of internal and external angles relating polytopes from the lowest dimension all the way up to, so these are all faces starting on the k dimension, so the lowest dimension of the polytope Q. We're looking at k faces of Q, and then you look at the angles between those faces in the lowest dimension and higher faces, where we go by steps of 2 for all faces between k all the way up to capital N. And then we again compare the internal angle for those interior to the higher. So we end up with a factor looks like this. We saw on Monday. We also end up with factors very similar to what you would have seen from Martin Wainwright's talk in the later half, where he was talking about the overlapping of support sets. So this would come out as a very natural aspect of this bound as well. And what we're going to do is we're going to do large deviation analysis for 2 polytopes of interest. First of all, the L1 ball. This is, of course, of interest. But we also can take a look at what's happening for the unit simplex. So this would indicate the case where you knew a priori that the coefficients were all of one sign. You knew the sign pattern beforehand. And we will look at the exponential behavior of these quantities in capital N because we know that the number of k faces is growing exponentially. So that's the proper scaling to look at the discrepancy. Okay. So here's the kind of results, and this is connecting back with the idea from neighborliness. So this is not the same phase transition I showed before, but a slightly different phase transition. The plus minus here means that we're looking at the unit L1 ball. So we're looking at the cross polytope, C capital N, and we're asking, when do we have all of the faces surviving projection? So here would be the statement: with overwhelming probability on the selection of A, this is our random ortho projector. When we solve the L1 problem, we're going to in fact recover the sparsest solution for all signals, not a preponderance, but literally for all of the signals, provided the sparsity is sufficiently low, and sufficiently low is a constant here multiplying little n. So this is as high of a result, as strong of a result as we could hope for, with this constant here telling us what the constant of proportionality is. And this constant is this plot here. So this blue line is rho s plus minus. If you recall the prior slope that I was talking about with neighborliness, this is the same kind of plot. For neighborliness, we were looking at the case where the signals were all of one sign, which also corresponds to if you were having Gaussian random points thrown out in our little n. When you're talking about cross polytope, it doesn't correspond to Gaussian points anymore, but to a random ortho projector. To quantify the statement a bit, what we have is that for k less than that constant, the discrepancy between the number of faces of the L1 ball in dimension capital N and the expected number of faces of the randomly projected ball is given by a quantity like this. So a polynomial in little n times an exponential factor with a constant here, which is related, of course, to how far below this curve we are. So there's a relationship between epsilon and epsilon tilde that we'll go at in just a moment. One could also read this in terms of saying that the probability once you are below this curve that the expected number of faces, or that the number of faces you have is exactly the number of faces you started with, goes to 1 in this asymptotic limit as capital N goes to infinity. Okay, so what exactly did we prove? How strong are these results? Let's go into the details for a moment. Okay. So in the large deviation analysis, we end up with bounds like this. We, of course, look at bounds on the expected number of faces that are lost from above. We get an exponential factor here. This is what we're interested in. But we also compute bounds from below to make the results sharp. And the important point is that the exponential factor, which is really going to control the behavior of this phenomena, is appearing in the exponent. It's the same factor. Okay? So how did we derive these thresholds? Well, that's really just the level curve for this function here. Okay? So our strong threshold is the 0 level curve for that function. Here's a plot for what this function looks like, what this psi looks like in the case of the L1 ball. So below this curve, it's strictly negative. Above the curve, it's strictly positive. You can see that it's primarily very negative here, but becomes slightly positive here. Not strongly positive, but slightly positive. However, even being slightly positive is sufficient to guarantee that if you're above this curve, then this bound guarantees that the expected number of faces that you lose is in fact exponentially growing. So it's certainly not 0. You will in fact be losing faces. However, if you fall below this curve, then this will be strictly negative, and you will, as capital N goes to infinity, the expected number of faces that are lost will be driven down to 0, showing the sharpness of this phase transition. Okay, so you might ask, well, these are asymptotic results as n goes off to infinity. How strong are these results? How does this behave really as we go slightly below? This is the kind of question that an engineer would certainly want to know. So we have bounds on those kind of things. So you could ask, okay, let's let k be proportional to little n, and then we have our phase transition. We're going to go below the phase transition by a multiple, 1 minus theta. And we want to understand how this theta dictates the convergence rate. Well, the theta here is given by the bound from above. We're only going to look at what's going on below. We're really only interested in when it works, not so much in when it doesn't work. It's good to know that it doesn't work there, but precisely how badly it doesn't work isn't of such interest. So we look at the discrepancy here, and we get a bound of this form, and the theta appears with little n here, okay, the theta, not capital N, but little n, and then a function here which depends upon the undersampling ratio Now, for the L1 ball, we have what this thing looks like. That would be the, let's see, I guess that would be the dashed curve here. And for the unit simplex, we have the solid curve here. In both cases, it's interesting to note that this is bounded away from 0 by a half, and that occurs here. In this limit, as little n over big N going to 0, it in fact converges down to a half. And if you looked, another way of interpreting this would be to say, if we fixed a probability here that we were okay with, and we were then to, so we have a fixed level curve that we're interested in, and then we're going to grow our variables, we could ask, how rapidly does a fixed level curve converge to our asymptotic limit? Well, it converges at the rate of n inverse, at 1 over n, because the n and the theta here are multiplicative. Okay. So once we have very precise statements like this, we can make statements for finite values even. We could, in fact, be looking at these kind of polytopes, and we could ask, tell me the domain for which there is a non-vanishing probability. So there's a probability that there is a polytope that we're going to pick, a random projector, so that it does have k neighborliness. So what is the domain that there exists such a thing? So if an engineer were saying, I'm going to look for constructing a matrix that has the property you want, and I'm going to look at it with this value of little n, little n, big N, you could say, well, this is how far you can push k. We'll give you a region for which you could actually look at the problem. So n being 200, 1,000, 5,000, and n off to infinity. And infinity is, of course, the asymptotic limit. That's given in black here. This is what we saw before. For the finite values of even, say, n being 200, the results, the bounds are quite strong, and we get a curve quite close. Now, n being 200 is extremely small for applications. Now, notice on these curves that, in fact, these phase transitions do run into 0 for finite values of n. That's not such a surprise, because if we let little n go down sufficiently small, we're not really talking about a high-dimensional phenomena anymore, and we shouldn't expect that we would be getting this sort of neighborliness property. Okay, so that's a rather strong statement that we're looking at, where we want essentially that you solve L1 and you get this partial solution all of the time. But for many of you who are working on applications, this probably isn't what you're really interested in. Instead, you probably want to know simply when is it going to work most all of the time. You're going to be running some experiments, and you want it to work all the time that you care. Not all the time, but just most all the time. So we're going to weaken our conditions slightly and ask when we're going to get recovery for most signals. Okay? This is the kind of result that we will come up with. So if we have k, again, up to a constant proportional to little n, we should expect that we're going to have a constant proportional to little n, because this phase transition has to be higher than the strong phase transition. We're going to look at when there's a discrepancy between the expected number of phases which survive projection and the number of phases we started with. Oh, that little l should be a k. Sorry about that. So we have an epsilon tilde here. This could be extremely small. So it's a vanishingly small fraction of the phases that we're allowing to fail. Not a large number, but a vanishingly small amount. Then with overwhelming probability on the selection of A, overwhelming probability will quantify what that means. The L1 will recover L0 for most x, for most, not all, provided we're below this threshold. Well, how do these thresholds compare? Well, this is the curve in the case of the L1 ball. This bottom curve is the one we've seen before, where we were looking at having it work all of the time. So this is the strict neighborliness phase transition. Up here we have the weak neighborliness phase transition. This is when we're wanting it to work, in fact, most of the time, not all of the time. And we can see a substantial increase and something noticeable going on down here. So both there's a substantial constant increase for a fixed ratio, and also something going on in the ratio as little n over big N goes to 0. Okay? So again, if you wanted to ask, well, how is the success rate as you move below the phase transition curve? Well, we know these kind of results as well. If you have a multiplicative factor, 1 minus theta times the phase transition, so you're going below by a factor of 1 minus theta, then the fraction of phases that are lost, this is the number that are lost, and then we look at the fraction, is being bounded by a polynomial again, We have explicit statements for the polynomial and an exponential factor, and this exponential factor is little n times theta squared, so theta squared instead of theta, times another factor here. This factor is, again, a function of little n over big N. We can see what the factor is. So for solid, this is for the unit simplex, and the dashed line, which is lower, is for the L1 ball. Again, in one of the regimes where we have most interested in is what's happening as little n over big N goes off to 0. And in that regime, this is converging to a quarter from above. So these are strictly bounded away from 0 by a quarter. So if you wanted to simplify this lemma, you could remove this and just put in n theta squared divided by 4. One could also interpret this by looking at the behavior of constant level curves for a given success rate, and then how rapidly do they converge to the asymptotic limit. So again, we have here not n times theta, but n times theta squared. So the convergence rate for a fixed level curve will converge at the rate of n to the minus a half. Okay, so we could again ask very precise statements for finite dimensions. We could say on this curve over here, for instance, we want to be looking at the regime where we're going to construct we're going to draw a random orthoprojector, and we want that in expectation, 99% of the faces survive. So if we were to use this for our application, 99% of the time we would be fine. And we could look at various problem sizes, tiny problem sizes of n being 200, up to larger problem sizes going off to the asymptotic limit. So the black curve is again the asymptotic limit. Blue curve is at 200, 1,000, 5,000, and then off to infinity. Now, another difference between this kind of a phase transition and the strong phase transition is that we can just test this phase transition out. We can't really test out the strong phase transition because testing it requires literally trying all possible support sets, which is an NP-hard problem. So can't do that, but here we can just try it. We can say, maybe we're not going to see the exact convergence rate as we move away from the phase transition, but we can try meshing up the domain of k over little n and little n over big N. We can try various values of this triple, k, little n, and big N, and we can try the problem, construct a k-sparse vector, multiply it by a, get b, and then try to recover x back from this, and record what fraction of the time it's successful. So here would be for a very small example. So we're looking at n being 200. We mesh up the domain. Here, little n over big N, k over little n. We mesh it up. I think it was something like a 40 by 40 mesh. And for each test point, we try something like a few hundred, maybe 1,000 tests. And we see that in this domain, it's working essentially all the time. So the fraction of times that it works would be, in fact, 1 down here. As you move up, it begins to decay. And then you see the 50% curve of success is very, very similar to the asymptotic phase transition that we're showing. So here, this black curve is overlaid here in red. And you can see this going from working all the time to failing. And you can see that even for very small values, we get extremely good empirical agreement, would match what you would actually see in practice. Okay. Now, Emmanuel mentioned, and I believe Dave mentioned as well, this very interesting new topic of compressed sensing, which is really making some waves in the signal processing community. Compressed sensing is really talking about essentially what's going on in the regime where little n is much, much less than big N. So in that setting, essentially you have a signal which you want to sense, which is x, and you make the measurement by applying a to it. And a is of size little n over big N, so the number of measurements you're making is little n. The way the measurements are made is via inner products, and you then want to try and do recovery. So you would like the number of measurements that you're making, little n, to be very small compared to the signal length. You'll notice that in these plots that as I'm showing, this regime of little n over big N, these curves are all diving down to 0. And what we would like to understand for compressed sensing is the rate with which they're approaching 0, so that we know how well the compressed sensing algorithm is going to work. Now, at the beginning of the talk, we talked about some of the classical results where you fix little n and then you let big N grow. You keep adding more and more points, and it was very clear that it's not even going to be 0 neighborly. Things are not going to work if you add arbitrarily many points. But if you control the rate with which you allow this variable to go to 0, So we're going to have little n and big N going to infinity. They're both growing, but potentially we could have capital N much, much larger than little n, not just a constant multiple larger, but it could be, say, e to the square root of little n. So much, much larger. That would be fine. So we're having this go to 0, but this ratio also needs to go to 0. So we can't have arbitrarily more, but we can have a lot more. In that case, these phase transitions have very precise behavior that they converge to. So asymptotically, the strong phase transitions converge to a factor which looks like 1 over 2e times a log of capital N over big N. There's a correction term and an offset. The techniques will allow you to even recover those kind of quantities. But essentially, the main point is 2e times log of delta. This would be the kind of phenomena that we were seeing in Martin Wainwright's talk, where he was talking about essentially sensing what was going on in the asymptotic limit for little n over big N, and also in Emmanuel's talk again, the statements saying that compressed sensing is within a log factor of optimal. This would be the log factor, and it's corresponding to this regime where little n over big N is going down to 0. The weak threshold has a very similar formula, but the 2e is replaced by a factor 2. Okay? So the principal difference in those cases is just this multiplicative factor e. So if you had made some number of measurements, and it was not working well, so it was working most of the time, but you wanted to ensure your success rate to all of the time, you'd need essentially an e times factor more measurements. So I would say that at this point, we've quite well characterized what's happening for a lasso in the noiseless case. So essentially solving for L1 without noise in the with our model A being Gaussian. One of the very interesting things is that this seems to be, the results that we've uncovered seem to be more universal to a broader set of matrix ensembles. It's not exactly clear why. We're working on that. We hope to have some answers before the end of this, this program here at Cambridge. So here's a plot that Dave put up. Let me describe again the kind of results that we have. So this is one of the weak phase transitions. This is the weak phase transition where you're looking at projections of the L1 ball. This is the weak phase transition where you're looking at projections of the unit simplex. The black curve, which is the dominant curve that you see, is the asymptotic limit. So we know what the asymptotic limit is for Gaussian. And when we try it for Gaussian, doing empirical testing, we see here a red curve sort of wandering. We can see it slightly better here than we can up here because this, we're looking here at, I think capital N is 1,000, something like this. And we know that as we go down towards a little n that the variance is going to increase around here. So we can see the results for the Gaussian, and it matches extremely well with the asymptotic results. That's not surprising. That's essentially confirming the theory that we developed. What is more surprising is that if you try the same phenomena for matrices whose entries are drawn uniform 0, 1, or if you look at partial, so random rows of a Fourier matrix, or if you look at Hadamard matrices, or if you look at, in fact, things like Kurdock codes, which are entirely deterministic, they all seem to behave empirically on these phase transitions. So you can try it out. You can see when it's succeeding. In this domain, it'll be succeeding. And as you approach this curve, it'll start to fail. You'll have the curve coming down, similar to what you would have seen in Martin's talk. And then it will reach 0 at this point and be essentially 0 above. OK. So as a few kind of takeaway statements, one could ask to sort of wrap up the results. How many random projections are needed to recover a k-sparse vector of length capital N? Well, with overwhelming probability on the selection of your your measurement matrix, you can recover all signals provided the number of measurements is greater than 2e, so a multiplicative factor about 5.5 times the information content k times a log factor capital N over little n. If you want it to work most of the time, it's like 2 times k times a log factor. Remember that the upper bound on neighborliness, strict neighborliness being twice, one would not really expect to overcome something like 2k. So this is very close to as good as one could possibly hope. Okay. You may have also heard of these results being applied for construction of error correcting codes. I think Emmanuel may be the first person who pointed out this phenomena. It's very cute. So since we have a few minutes, let me sketch the way that this works. So take a unitary matrix. very easy. This is essentially a corollary of the kind of results that one gets in sparse approximation. So we decompose our n by n unitary matrix into size little n and capital N minus little n. And then we get some data, which is in our capital N minus little n. And we would like to communicate this information to someone, so we're going to send this information. Is it difficult to see with this? Thanks. So here's our data. We want to send this, and we need it to be robust to errors. So we have to embed it into a larger signal. So what we do is we send b times data. So this is the data that we're going to send. This is in, b transpose times d. This is in our capital N. So we've embedded it into a vector which has little n more entries, and we would hope that maybe we could correct little n errors somewhere. This would be our goal. What we receive isn't going to be this, though. So we receive a signal which is s plus some corruption. And this corruption in this view is not going to be, say, Gaussian random corruption, but is going to be spike corruption. So we're going to corrupt a few entries, potentially very badly, potentially maliciously, but just a few entries. And what we do is we simply apply A to the data that we receive. We apply this to S. And note that by construction, from this being a unitary matrix, A times S goes to 0. We have this as our data, and we're looking for eta. So what do we do? Well, we solve min the L1 norm of eta subject to A eta is equal to A times the signal that we recovered, and this is our known vector. And you can see that, of course, if eta is sufficiently sparse and we solve this problem, we will recover our sparse vector. The case where we were looking at before of little n over big N going to 0 could be viewed as what's happening for essentially highly efficient error correcting codes. So we want to have little n, the number of additional terms we're adding to our code, be very, very small compared to the length of the code. And in that case, we get recovery provided we have not little n number of errors, but little n divided by a constant, 2 times log n. In the case where the errors are sort of random, the support set where it's selected as random. Alternatively, if someone knew how we were doing this, they knew what our matrices were, they knew everything about what we were trying to accomplish, provided we didn't allow them to corrupt more than little n divided by 2e times this log factor of big N over little n, they would, again, not be able to corrupt our signal, and we would be fine. The error correcting codes would work. So as a summary of these results, we were looking at the underdetermined system AX equals B for any domain of little n less than big N, provided we don't have a exponentially smaller little n. Then if you solve the L1 problem, you will recover the sparsest solution provided you're in the appropriate domain given by these phase transitions. We know the phase transitions for strictly recovering all the time. We know them for recovering most of the time. We know what the behavior is in the compressed sensing regime where we're letting little n over big N go to 0. We know what the constants are very precisely. And again, this log factor is what we were getting from the oracle rate. I'd like to wrap up with a quick slide comparing this with some of the other results that we've seen here. So Martin gave a beautiful talk on Monday where he was looking at the behavior of lasso with noise. And he was looking at the case where the coefficients in X were bounded away from 0 and wanting to see what the phase transition behavior was. And he was referring to it as a scaling so that he could get his curves to line up on top of each other. Well, the behavior he was getting was this ratio of little n over big N being proportional to twice in the Gaussian, this was in the Gaussian case, twice times log of big N over little n inverted, which is very similar to what we recovered, which is twice log of capital N over little n. Very, very comparable. And he discussed some of the differences between what's happening with capital N minus little n and capital N over little n, and showed that the best one can really hope for is to have capital N over little n. We are obtaining that in the case without noise. There's another way that a lot of people have been looking at sparse recovery. It's very natural phenomena, probably the most natural way of looking at sparse problems in general, and that is the restricted isometry property. So what is a restricted isometry property? First of all, this was by Condes, Romberg, and Tau. Well, the restricted isometry property for vectors with k non-zero entries would be to say that if you have a vector x with k non-zero entries, when we apply a times that vector, that in the 2 norm, it doesn't really change the scaling very much. It scales it by, say, 1 plus delta or 1 minus delta. So you could look at these as frame bounds if you're in approximation theory, or bounds on the eigenstructure. The kind of results that one can get out of the restricted isometry property are quite similar, but a bit weaker. So you can show that, in fact, L1 will recover all L0 for all vectors. So traditionally, these kind of results are for all signals, not for most signals, with a probability that is, again, exponential in capital N, provided you're below a certain threshold. Where the differences really come into play is that the constant is not going to be accurate, essentially. The constant is going to be relatively close, but it's not really going to match what you would see if you were to actually try it out. If you were to do empirical testing, the constant would come out as being off. So the constant they get is something like on the order of 7. Now, that's not so surprising because this is really a much more general tool. Right? This isn't really tailored specifically to L1. And in fact, this can be used to look at the behavior of other algorithms, but it can't recover quite the same kind of accuracy that you could using the theory of polytopes. Not exactly surprising. So to finish, here are the series of papers that most of these results are contained in. Some of these were results that Dave and I did together, and some of these are results that Dave did before I joined him in the project of the polytopes. Also, if you're looking for a great paper to read, let me suggest the compressed sensing paper, really the best paper I've read. And many, many people are working in this area. This is just a very small subset. I apologize if you're working in the area and your name is not up here. Some people are working on this from ideas of geometric functional analysis, such as Rudelson and Vishinin. Some people are looking at this kind of problem directly in terms of polytopes. So Linial and Nowak have some recent results looking at how neighborly heterosymmetric polytopes can be. So that would be the projection of the L1 ball. And then there's a whole slew of people working on compressed sensing. Some of the experts are here. Emmanuel, of course, Dave, the 2 inventors with Tau, Romberg and Tau, looking at various aspects from applications, single photodiode camera, to various other algorithms, OMP, which is a greedy algorithm. Dave discussed phase transitions for a variety of different kind of algorithms beyond L1. Various people looking on applications for MRI, things such as channel estimation, radar, you name it, it's out there. I think that's it.
Any questions?
Neighborliness, of course, is extremely important for best batch searching and so on. What's your view of going to multiple polytopes, multiple Gaussians, far more complicated inherent shape?
So you would be saying where you're having, I'm not sure I understand exactly what kind of, when you say 2 polytopes, what exactly do you mean?
For instance, to begin with, multiple Gaussians, dumbbell-shaped configurations.
Oh, I see. So they could potentially have different means.
Absolutely.
Well, I think that would, you probably wouldn't be getting, I don't think you would be getting strong neighborliness, because once you, if you were looking at, say, the projection of the L1 ball, you would have mean 0 included. And then if you had some other mean, you have some other mean, and the points that are in between are going to be obstructing some of your faces. So you may have weak neighborliness that one could investigate in that case, but the notion of strong neighborliness probably wouldn't be fruitful.
You get extremely strong and very fine results, but suppose I was trying to look at it from perhaps a softer angle.
Mm-hmm.
So the way people usually address phase transition in fields like percolation, for example, is via the Kolmogorov-01 law, where you have an event that you're interested, for example, all phases are conserved, or 99% of the phases are conserved. That's an event. and you show that somehow it obeys a Kolmogorov 0-1 law. What, is this, and of course they would not give the very fine result that you're discussing, but perhaps since you're mentioning universality and things like this, is this something that is useful to think about? Like the role played by things like, so for example, if you think that the number of measurements and the dimension of the signal go to infinity in a fixed ratio, then it seems to me that this is a place where the Kolmogorov 0-1 law would apply fairly naturally.
Not being so aware of the techniques, I don't know whether they would be able to give you such precise constants.
Of course not. No,
So,
they would explain the phase transition.
The question really isn't the phase transition. With the weak universality conjecture, we're not saying we believe that there's a broad class of things such that it works within a log factor. We're saying we believe that there's a very broad class of matrices, including some class of deterministic matrices, so that these are the exact phase transitions with these exact constants. Not that it's somewhere, but exactly that constant.
I understand this completely. I'm just wondering, like, if I were to explain why there is a phase transition to someone who may not know so much about polytopes, maybe one way to say, intuitively there is a phase transition, perhaps because of something like the Kolmogorov 0-1 law. That's all what I'm saying.
Sure.
Of course, I'm talking at a much lower level here.
Yeah, that's certainly possible. Yeah. But we've been looking at this question a little bit, and we think we have some avenues to try and prove the universality.
Because like when you look at statistical physics and work there, whether there's a path connecting one, the graph, typically that's one cute way to get easy answers, but not very fine answers the way you get them.
So the very fine answer, it turns out there's essentially 2 degrees of fineness of the answers that we're getting. Remember, we were essentially doing the large deviation analysis and looking at this exponent. The answer that you get for the strong phase transition really depends fully upon the behavior of that exponent. The weak phase transition, it turns out that some of the intricacies in that differentiate, say, the case where all the entries are of a known sign versus random sign, that difference really drops out. And this may allow us to use approach possibly not so dissimilar to the way that Martin was looking at things to prove the universality. Sure, Dave?
On Emmanuel's question, I mean, a lot of the methods of statistical physics are kind of based on low-dimensional intuition, so percolation and things like this, really about the behavior of paths through 2- and 3-dimensional lattices and so on and so forth. And there's a way to look at what's talking about here is that if it were connected to statistical physics, it's like statistical physics in infinite dimensions. And it's all statistical physics where all particles are the same distance from all other particles. And so it's not a low-dimensional like percolation thinking. It's sort of very high-dimensional thing. And statistical physicists do study such things. So there are these, the spin glass due to David Gross, which is an example of that. And, it's just a different kind of phenomenon. And then the feeling of like using ergodicity and the long run and so on. If you were in low dimensions and you were dealing with an assembly of particles that were spatially distributed, so that you were studying, chunks of space far apart don't interact. So then you have the feeling that ergodicity and all of these things like mixing and so on could be present. When all particles interact, because you have an infinite dimensional interaction, then the chance of mixing or any kind of loss of influence with distance has gone away. And so the sort of high dimensional interaction case is somewhat different.
But if you take if you take a matrix with I, the entries, somehow you could establish that as the dimension grows, if you perturb a small number of entries, it doesn't affect the event that faces are conserved just by perturbing, then maybe you have a 0-1 law there. I mean, like, that's the spirit of the Kolmogorov result. If it doesn't depend on a small subset of entries of the projection matrix, then usually the thing, that was just a comment. So for example, if this were to work, but maybe it doesn't, then you could very quickly argue that for many projection matrices, then you have a fixed notation.
Okay.
Any more comments, questions? If this is not the case, then thanks again.
Thank you.